And hello again. So I'm going to be making some changes to the videos from here on because I was trying this new medium of recording the videos, and it was actually sort of boring me to tears the way I was trying to get it out precisely correct and doing multiple takes to make sure that everything was right on when I would write it down on the whiteboard. But what I'm going to do now is I'm going to try to kind of format this like I do my lectures when I'm on the board. Um, my lectures are extremely high energy. I typically feed off of the students' energy in the room as well, but I'm going to try at the very least, even though I don't have that going, that kind of feedback system going right now, I'm going to try to uh, just share with y'all some of the love that I have for machine learning. I'm doing this because I love it deeply. It is the most fascinating subject I've ever studied. So um, I love sharing that with everyone. So these videos, I'm going to attempt to have much more energy, and we're going to tackle the topics. If I mess up, I mess up, move on, no big deal, but hopefully they'll be a little more enjoyable to listen to, and we'll go from there. All right, so today we are starting off with a very fascinating topic. We are going to be talking about linear regression where we have more than one variable. So in the past, we were just doing the square footage as a predictor for the price, but now we are going to be doing many features for the price. And so that leads us to multivariate linear regression. So that's where we're headed today, and we're going to start off with looking back at what we had with linear and then how that will change as we moved with rather single variable linear regression, and now looking at how that will change as we go into the multivariate. So we started off with the simple linear regression. We had our hypothesis function as theta 0 plus theta 1 x. And so our x was our feature, that was our square footage. And then our h of x was our predicted price, right? Our y hat. So that's what we started with, and the only feature that we looked at was square footage. And as a matter of fact, our simple example, that was a 0. So all we had to worry about was finding the parameter theta 1, which turned out to be not that hard. So now, though, as we increase the complexity of the model, things are going to get a little more complicated. So we're going to start off with a table where we have more things than what we used to. I'll just start right here. So we're going to start off with what we had before, which is going to be the size and the square footage. Then we're going to have the next one, the number of bedrooms, and then the number of floors, and then the age of the home, and finally, we're going to have our predicted price. Okay, so these are just going to be some sample values. Size is going to be our x1 feature, x of 2, x of 3, x of 4, and then we're going to have our predicted y, which we can sometimes call y hat. So the values might be 852 to 1 floor, 36 years old, and maybe the price is 178,000. Oh yeah, let me put this up here. It is in thousands of dollars. So, alrighty. Maybe another example, 1534. 3 bedrooms, 2 floors, only 30 years old, and now it's bumped up 315,000. And finally, let's say that we had 1,416 square feet, 3 bedrooms, 2 floors. Maybe it's 40 years old now, and it's worth 232,000. Okay, so we now have this nice little table of all the different features our 4 features, and that's going to help predict the price a little bit better. Now, if we have 4 features, I need some way of denoting the number of features in my code and in my algorithm, so n is going to serve as the number of features. The number of training examples, if you remember, was m, and n is reserved for the number of features. Okay? We're also going to be able, since we have multiple x's now, we are going to, this is going to be a little bit strange, we're going to say x superscript I sub j. This is the jth feature of the ith training example. Okay, let me clear the screen and we will kind of dive into that a little bit. So let's see if this works. Magic. All right, turn the page of my notes and here we go. So in the previous example that I had, if I had looked at just x superscript 3 with no subscript, that would have been the third training example, and it would have looked something like this if we think of it in terms of a vector. 1,416 square feet, 3 bedrooms, 2 floors, and 40 years old. Okay, this gives us a 4x1 vector, and if I wanted to access an individual feature within this training example, let's say I wanted to do x sub 2 of the third training example, well, that would just be the 3 right here. All right, so this is the notation that we're going to be using for our new features, the multiple features inside of our example. And since we are now completely changing all of this, we're going to need a completely new hypothesis function. But I bet you can guess what it looks like, because I need a theta 0. That's going to be my offset, my y-intercept, plus theta 1 x1 plus theta 2 x2 plus theta 3 x3 plus theta 4 x4. Okay, so what I have here is all my different features, and these thetas are what? What did we call those thetas? The thetas were our parameters. Those were our weights, right? The whole name of the game for running this algorithm is to determine what the weights are going to be that modify all of our features. So h of x is going to be our price. I can put that right here. This is our y hat, our price. And now I need to know what each of these thetas, how they modify the individual features. As an example, maybe I have h of x is equal to, let's say I've run the algorithm several times and I've found out that my parameters are 80 plus, oh, I don't know, 0.2 x1 plus, I don't know, 2.4 x2 plus maybe 1.7 x3 minus 2 x4. Okay, now what is it? What does all this mean? Well, first off, let's talk about 80. 80 is the kind of the bare basic y-intercept. When all of these values are a 0, the very base level value for a house is 80. So you kind of think that as the bottom market price, or it can be thought of as kind of like the baseline value. And it's not true that if we have a 0 square foot house with 0 bedrooms and 0 floors, that is 0 years old, that we're going to be able to sell a house for 80,000. But it does give us sort of an indication of the market value. If this is a high value, let's say 300, odds are the market is pretty high for your housing. If this is a low value, say 10, it's a very low market. So this is kind of an indication of where the market is, the overall market. Now, this 0.2 is modifying x1, and x1 was the size in square feet, right? And that kind of makes sense. If I have 1,000 square feet, this says that it's going to modify it by 200. Okay, I'll accept that. Not too bad. And then if I come over here and I look at x2, what was x2? x2 was the number of bedrooms, right? And it's worth 2.4 thousand per bedroom. Okay, I'll buy that. I think it would be a little bit higher, but that's okay. X3, we have the number of floors, which again, 1.7 I think might be a little bit low for how much that would influence people buying a house, but okay, I'll buy it. Finally though, the one I really like to talk about is this X4, the age. Notice all of these values are positive, and this is the only one that's negative. Why? Because, and of course I waited expecting someone to answer me. Maybe y'all did. Maybe you spoke out loud. I'll accept that and run with it. So the reason this is a negative value is because as the age goes up, the value of the price goes down. So if we multiply this by 50, if let's say the age is 50 years, we've lost 100,000 on the house value. And I'd say that's probably fair. So this is our new hypothesis function that we're going to be using to actually tackle the new algorithm to find the best fit. It makes kind of a general sense, and I think I believe it for now. So before we can go any further, we need to do a linear algebra overview. So buckle up, we're going to do some linear algebra. Okay, so before we get to linear algebra, I need to talk about one thing that I haven't quite referenced. I forgot to reference, and that is we had that pattern real quick. H of x is equal to theta 0 plus theta 1 x1 plus ... all the way out to theta 4 x4, right? And every one of these thetas had an x that went with it. But theta 0 here had nothing. It was just theta 0. But what I want to do is say that there is an x here. We're going to call it x sub 0. And the way we get away with this still remaining a value, just a number here, is that x sub 0 is always going to be thought of as a 1. Therefore, it's okay to say theta 0 plus theta 1 x1 ... all the way out. It's also okay to think of it in terms of a vector. So if I think of in terms of an x vector, we have a column vector. We got x0, x1, x2, x3, and x sub 4. Okay, that's the x vector. And so if we have n features, this is an n plus 1 because we have the x sub 0 times 1 vector, right? Okay, now let's move over to the theta vector, and that's going to be, well, very similarly, theta 0, theta 1, theta 2, theta 3, and that's a 3, I promise, right there, theta 4, okay? So that is our theta vector, and it is also an n plus 1 by 1 vector, right? The number of rows by the number of columns. Rows, column. Well, I only have one, but that's okay. Okay, that's how you reference your vector. Now, what we're going to do is something kind of odd, is we're going to transpose theta, okay? So if I look at the transpose of theta, theta transpose, the way that you think about it is, if you will, I'm going to write it over here, theta 0, theta 1, theta 2, theta 3, and theta 4. The way you can kind of think of doing a transpose is you are turning a column vector, in this case, into a row vector. You're taking the indice for the rows here, so this is row 1, row 2, row 3, row 4, row 5, and taking that indice and instead putting it as the column 1, column 2, column 3, column 4, column 5. I mean, you can kind of imagine that if I rotated it in space, so I kind of rotate around, swing this top down, I'll get the same, what I'm looking at right here, which is my row vector for theta transpose. That's all I'm going to belabor that, because what that does is it gives us some really nice properties. Because if you remember, for matrix multiplication, here we go. Let's say I have something not so bad. Oh, maybe, I don't know, 2, 1, 3, 4 times, let's go with maybe 2, negative 4. Okay, this is a 2 by 2. This is a 2 by 1. As long as the interior numbers in a multiplication match, you can multiply them, and the result is always going to be the outermost values for our what we denote with the matrix size. So this should wind up being a 2 by 1. And the way you do it is you take the first row, so this first row right here, and you multiply it after rotating it by the first column over here. So in this case, we're going to get 2 times 2 plus 1 times negative 4. Okay? After we have sent the first row through the first column, if there were a second column, we would send it through that, and third column, so forth and so on. But since there's only a single column, that's where we stop. And then now we move down to the second row right here. So we take that row and we multiply it through. So I'm going to get 3 times 2 plus 4 times negative 4. Okay? So when the dust settles, I'm going to wind up with 2 times 2 is 4, plus negative 4, 0. 3 times 2 is 6, plus negative 16, negative 10. I hope I did that right, but I will not guarantee my math works out. I am definitely prone to simple mistakes when it comes to math. So this is the basic review of matrix multiplication, and the reason that we're setting this up is so that we can use our x vector and our theta vector, and especially in terms of theta transpose. So let me clear this, and then we will knock that out. So I have that my theta transpose is equal to theta 0, theta 1, theta 2, theta 3, and theta 4. Now if I multiply that by my x vector, which is x naught, x of 1, x of 2, x of 3, and x of 4. Okay? This right here is a what by what? It is a what? It's a 1 by 5, and this one is a 5 by 1. The inner values match, so we know that we can actually multiply these two things together, and the result is going to be a 1 by 1. So what does it look like? Well, when we do our multiplication, we take the row, this row right here, and we kind of shift it over and multiply with the first column, adding each one as we go. So theta transpose x is going to be theta 0, x0 plus theta 1, x1 plus theta 2, x2 plus theta 3, x3 plus theta 4, x4. Now, this theta transpose x is way more compact than writing all this out. And you can definitely imagine if we had, 60 features, I do not want to write out theta 0, x sub 0, all the way up to theta 60, x sub 60. Instead, I just have this nice little expression, theta transpose x, where theta transpose is a row vector, x is a column vector, and we just multiply the two to get this nice summation. And that's exactly what we want for our hypothesis. So, with that in mind, I can now say my h of x is just theta transpose x. Done. I like that. Very nice, very compact. Okay, so the next thing we're going to do is work on our cost function using this new hypothesis function. All right. Okay, so now we're going to talk about our new cost function. So we have j of theta is just equal to 1 over 2m summation I from 1 to m of, we have our hypothesis function, xi, and minus our yi, quantity squared. That's just the MSE again, right? So what I'm going to do is I'm going to expand out this new hypothesis. So if I do that, I get j of theta is equal to 1 over 2m summation I from 1 to m of, here we go. We're going to have, I'll put a bracket right there. Here we go. Theta 0, x sub 0, plus theta 1, x sub 1, plus theta 2, x sub 2, plus theta 3, x sub 3, plus theta 4, x sub 4. That's my hypothesis function minus yi quantity squared. Okay, so the reason that I expanded this out is so that I can now take the partial derivative of my cost function and it'll make a little more sense what it winds up being. So I'm going to start off with the partial derivative of j with respect to theta 0. Okay? Well, partial derivative of j with respect to theta 0, we're going to have the 2 come down and cancel this 2. So we're going to wind up with 1 over m summation I from 1 to m of, we're going to wind up with the only thing that survives, well, first off, I'll do it all the way out first before I get to that. So this is going to be all of this h of x, right? So it's what's in the interior untouched. So h xi minus yi, and so that finishes that. The power rule becomes subtract 1 from it, so now I get to the first power here, and then I multiply it by the partial derivative of this interior with respect to theta 0. The only thing that survives is this term right here, where the only one that survives is x sub 0 I. So x sub 0 I. Oops, sort of like that. There we go. Now let's move into partial derivative of j with respect to theta 1? Well, that's again going to be 1 over m summation I from 1 to m. Nothing changes on the interior, hxi minus yi to the first power times, now what survives when I look at the partial derivative with respect to theta 1? The only thing that's going to survive this time is going to be x of 1, I. And I see the pattern. When it's with respect to theta 0, the only change in this expression is it gets multiplied by x of 0, which we know is actually, that's a 1, but we'll just leave it like this for now. When I take the partial derivative with respect to theta 1, the only thing that survives is x of 1. So now that I've got that, I can make a general expression. The partial derivative of the cost function with respect to theta sub j is going to equal 1 over m summation I from 1 to m of my hypothesis function hxi minus, whoops, I forgot my little paren there, minus yi times x of j I. So the partial with respect to theta 4 is going to be everything like this, like the standard one that is for every single one of them, times x of 4. So that's the way that it's going to work for every single one of my parameters. When I take the derivative of the cost function with respect to that parameter, it is the standard expression we see here, which is exactly the same as we had for the linear regression, times x sub j I. So that is our new and improved partial derivative. Okay? Where do we use that partial derivative? Well, we use that partial derivative when we talk about our gradient descent algorithm. The gradient descent algorithm is now going to say theta sub j is going to equal the old theta j minus alpha times 1 over m summation I from 1 to m of h of xi minus yi times x sub j I. And that is going to be our new gradient descent algorithm. And notice that we are going to be running it for every single one of our theta j's. Every parameter will go through this same process in order to arrive at the weights or our thetas. Okay? Now, with that in mind, let's talk about some of the pitfalls that can happen when we're trying to code this up. So here we go. Okay, let's say that we're in our code and we're going to have theta 0 is equal to theta 0 minus alpha times 1 over m summation I from 1 to m, and we've got of our h xi minus yi times x sub 0 I, right? And then we had theta 1 is going to equal theta 1 minus alpha 1 over m summation I equals 1 to m of h xi minus yi times x sub 1 I. Okay, let's say that we are running through this inner code. Oh, and I have a paren right there on the outside. So we're running through this inner code. I update my theta 0, then I update my theta 1, theta 2, theta 3, dot, 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 all the way to theta 4. And is everything going to be absolutely fine? No, we are going to have a big problem if we run this kind of algorithm inside of our code. We do not want to do this because if I run first time, when I loop through, when I do this line right here, I'm going to find a new value for my theta 0 and assign whatever this is over here to that value, theta 0. Then when I move down to my theta 1 and start to do that calculation, that new theta 0 is in here in my hypothesis function. It's hiding inside of that. So what will happen is the program will update theta 0, and then as I try to calculate my new theta 1, I wind up with an updated value in here. And so then when I do theta 2, well, you can imagine it gets worse, because now my hypothesis function over here would be a new theta 0 and a new theta 1. Both of those would be inside of this. So I can't run this type of update inside the code. Instead, what you have to do is change these values into temp values. Temp. Maybe temp 0. Let me write that out. That looks terrible. Temp 0. I definitely have theta on my brain. Let me try that again. Temp 0 gets theta 0 minus alpha 1 over m summation I from 1 to m of hxi minus yi times xi. Okay, so I use my old theta, I run through this expression right here, and I assign that value into temp 0. And then I do with the same with another temp variable. Temp 1 gets theta 1 temp 2 theta 2 Once I get all of the values, the new theta values assigned to all these temp variables, then I update as a block. I take all of these and update my new thetas with these values. Theta 0 as a block after I've done all my calculations. Theta 0 gets temp 0. Theta 1 gets temp 1. And theta 2 gets temp 2. And so forth for the entire block. So I do all of these assignments to temp variables as a block in my code, and then I move down to all of these updates to my theta values. Because I've finished all of these calculations, now it's safe to update them all at once. That's the correct way to implement it in your code. All right. Okay, so here we are in our code. We're in Spider, and as you can see, we're going to be implementing a very complicated model, and no, we're not. So from here on, we could do some code for the multivariate linear regression. It's not that bad, but one of the beauties of machine learning is for every model that you want to use to solve one of your problems, there's a library that you can call that will have that model, that you can pass parameters and have it do the work for you. You can write some of the simpler algorithms yourself, and it's not a bad exercise. And you saw before how we actually had to implement with the multivariate linear regression. But from here on, we're calling libraries when we're working with our algorithms. That's the standard way. And the beautiful thing about running in Python is is very well supported with tons of libraries. So that's what we're going to work with from here on. And we're going to start with from pandas, import data frame. So pandas is a library that allows you to work with data sets. It lets you import your data sets and manipulate them in a way that makes a lot of sense with the variables and the columns and everything. So pandas is how we work with values rather I should say, kind of spreadsheets of data where you have multiple types of data. If it's all numeric, we'll be using a different library called NumPy, but we have alpha and numeric mixed in, we tend to use pandas. So in this case, we're going to use pandas to import this data frame. The data frame is what we're going to have all of our features stored and all the values stored within. So that'll be the pandas. And then from sklearn, which is a wonderful library, we're going to import the linear model. So that is a linear model, whereas if you use one variable, it's a single variate linear regression, and if there are many variables, if there are many features, it's going to wind up being multivariate. So it just depends on the number of things that you pass to the linear model to whether or not it's the simple single variable or multivariate. In this case, we have a bunch of different sizes. We've got we start off with our few examples, 852, 1534, 1416 for our square footage, and I just added a whole bunch more. All the way out, there are 20 of these examples. And then I've got the number of bedrooms that correspond to those values, the number of floors, the age of the houses, and finally the price that they sold at. Okay? So with this, what we're going to do is feed this into the data frame. So the data frame is going to get this house features, and it's going to set the columns as size, num.br, num.floors, age, and price. Okay? Then for the input variables, the x variables here, we're going to have size, number of bedrooms, number of floors, and age. And for the y value, the predicted value, we're going to have price. And so all we have to do now is we're storing the model, if you will, the linear regression model from sklearn into this regra variable right here. And then we're calling regra.fit, and it's going to fit our inputs and to our outputs and try to find the line that best fits that. So after it's done, we can then call the results. The regra.intercept is going to be our theta 0 value, and then regra.coefficients are going to be all the values for our thetas, theta 1 through theta 4. Okay, so I'm going to run this, and hopefully we'll see it. Let me actually drag this over so you'll be able to see the results. So here we go. I'm going to drag this over where we'll be able to see in the console. I'm going to run it by pressing the green arrow up top, which is not shown, but it's there, I promise. I'm going to, oh wow, that didn't take long at all. Okay, which it really shouldn't with 20 training examples. So it found that the y-intercept was 80.79. So about 83,000 was our baseline, yeah, I think I called it baseline, price for a house. That kind of makes sense. And then we have that the size of the house, well, I mean, if I kind of rounded it up, it's about $100 a square foot. I'd buy that. That makes sense. The number of bedrooms was very important, way more than what I had initially in that. I think it was 2 point something like that. It was a single variable, but it's actually worth way more. The number of bedrooms is worth basically 54,000 each. And then we move over to the number of floors, which is also important, but not as important to the price. And finally, we have the age. You lose 3,000 on the price of the house for every year, which I think that's probably fair as well. That's it. That's how easy it is to run machine learning in Python. All you have to do is call your library and feed in your data appropriately to where it knows what to do. You then do your fit and print out the results, and that's it. It's that simple. So I hope you've enjoyed learning about multivariate linear regression. And for fun, if you'd like to, you can add other variables, other features up here. Maybe you want to add, gosh, I have drawing a blank. What's another feature about a house? Size of the front yard, things like that. And you could try that and see what kind of changes you would get for your different thetas. So things like that you can play around with. Feel free to change this data in any shape, form, or fashion that you want to. And I should also mention that if you want to make a prediction for any value, all you have to do is you've got this as your baseline. You're going to add this to whatever value you put in. This times your theta 1 plus this times your x of 1, this times your x of 1. These are the thetas. This times your x of 2 plus this times your x of 3 plus this times your x of 4. And it will actually predict a house for you, a price, I should say. So that's how it works. I hope you've enjoyed it as much as I've enjoyed talking about it. We will end here, and the next one that we do will be picking up with a different kind of regression, logistic regression, which is one of my favorites. So take care, and I will see you later.